Hello guys, welcome back to another segment of GGTutoring. Sorry that it's been a while since we made a video last time. It's just been pretty busy so far in the semester with midterms. So before we even dive into when we use an SN2 or E2, you need to have a good nucleophile. So what does it mean to be a good nucleophile? Basically, for a good nucleophile, there should be a readily available lone pair that can be donated, and should have a negative charge on this molecule to classify it as a good nucleophile. But not all good nucleophiles are good bases, or good strong bases. Every strong base is a good nucleophile though, so they're not really interchangeable. And this is important when we go into SN2 and E2 reactions. So I've written a lot of things for SN2 to kind of help you realize when we're actually able to use these. So SN2, this is not really important to know when you use it, but it's more just like a fact. SN2 reactions are one-step reactions that don't have any intermediates, and there's only one transition state. And basically the nucleophile just displaces the leaving group. But one of the main things that kind of tells you whether or not you're going to proceed via an SN2 reaction is sterics. So methyl groups are very favored for SN2, but the more substituted your alpha carbon becomes, the slower your reaction will occur by, and may favor other reactions out because your tertiary is also going to be the worst and slowest because you have the most sterics. Your alpha carbons will be very sterically hindered and make it very hard for your nucleophile to come in there and displace the leaving group. So tertiary is really not preferred for SN2. Whenever you have an achiral center or an asymmetric alpha carbon, there's going to be an inversion of stereochemistry from R to S or S to R, whatever. Every time you add the nucleophile and displace a leaving group, there will be an inversion. But if you don't have an achiral center, then there's no inversion that's going to happen. So only apply this when you have 4 different groups attached to your alpha carbon. And finally, polar aprotic solvents are preferred for SN2 reactions because whenever you have a polar protic solvent, there are hydrogen bonds that are there, and that can actually stabilize your substrate through hydrogen bonding. And that will basically raise the activation energy of the system and make the reaction much slower to proceed by. So polar aprotic solvents, where they don't stabilize the substrate, are preferred, so this reaction can actually proceed much faster. So knowing this, we can kind of apply this to the problem that I've drawn. So we see that this one's broken down into actually 2 steps. Not all SN2 are going to have 2 reactions that are occurring. It might just be one that's not labeled on the top, where the NaCl is on the top and DMSO is on the bottom. But for this one, this is more of a challenging one, which I wanted to include to kind of cover everything. So we see that we look at this and we're going to wonder, what is our nucleophile? The sodium doesn't really matter, it's just there for charge stabilization. So you have a chlorine that looks like this. It has lots of lone pairs and it's negatively charged. So we can already tell that this is probably going to be our good nucleophile according to our definition. And we want to know what's going to be displaced. And it's kind of obvious that iodine is going to be the one that's going to get displaced in this reaction. But we look at DMSO as our solvent, and we wonder, is this going to be a good solvent for SN2 or E2? Knowing DMSO, this is actually a polar aprotic solvent. Now we want to wonder for sterics if this is going to be favorable. So we look at our alpha carbon, which is the one that's attached to the leaving group directly, and these ones are beta carbons because they're the next one over, but they're not really important for SN2. But we see that this alpha carbon is secondary, so it's not really great, but it's not terrible either. But when we combine everything that we know about our solvent and our nucleophile, we know that this is probably going to go via SN2. So your chlorine is basically going to come in there, and it's going to displace your iodine. Right? So this is the first step that's occurred. So you're going to get something that looks like this. You're going to get an inversion of stereochemistry because your alpha carbon is attached to 4 different groups, which I'll circle. This is the different carbon, this carbon, there's an implicit hydrogen drawn, and this iodine is obviously different than all the other 3. So this is an asymmetric center, so there will be an inversion of stereochemistry, which is why we go from a wedge to a dash. But we're not done. In the second step, this sodium's also basically here for charge distribution, so it doesn't really matter. This is a very good nucleophile as well, so it's also going to displace this chlorine, which is also a good leaving group. So it's going to come here, the alpha carbon, and then knock off your chlorine. And you'll get something that looks like this. And that's basically your final product. The reaction mechanism for SN2 is actually very straightforward. It's just knowing when to use SN2. So if you look at the things that I wrote on the left, it's good to keep in mind when you're applying or looking at different problems. And if you can recognize some of the solvents you're using, your nucleophile, whether it's a strong nucleophile or a strong base, and the sterics that are associated with the alpha carbon, you can kind of determine whether or not you're going to use SN2 or E2. So that's basically it for SN2. So let's move on to E2 now. So for E2, strong bases are required. So that basically means that you already have a good nucleophile. But you want to look at that nucleophile and determine if it's a strong base or not. Also, polar protic solvents are more preferred for E2, unlike SN2. And there should be carbon-hydrogen bonds on the beta carbon. So our leaving group in this case has this problem that I've drawn. This is going to be our alpha carbon because it's directly associated to the leaving group. So the next carbon over is going to be your betas. Either way, it doesn't really matter which carbon it is. There's multiple beta carbons in this case. But now it says that the beta carbon hydrogen in the carbon leaving group must be anti-coplanar. So what does that really mean? So really to determine this, you can draw a chair conformation up here. So basically I've drawn all the main things you really need to look at. Your alpha carbon, your beta carbon, and your beta carbons. So anything that's going down is on a dash, and anything going up is on a wedge. So this chlorine is clearly on a dash because it's going down. So to know which beta carbon you're going to be using in this reaction, you're going to want to figure out actually which hydrogen is anti-coplanar. So to really determine that, you see that this beta carbon only has 1 hydrogen, and this hydrogen is going down. So both these hydrogen and chlorine are in the same plane, so they're actually not anti-coplanar, and we would not be proceeding via this beta carbon. But when you look at this beta carbon up here, it has 1 that is not anti-coplanar, but it has 1 that is anti-coplanar because it's going up. So we're going to use this beta carbon for our mechanism. So pretend that we have this substrate, and we're going to put it into NaOET and our solvent ETOH. As I said before, that Na is really just there for charge distribution. So this is going to be your nucleophile. And when you look at this nucleophile, not only is it a good nucleophile, it's also a strong base. And when you look at the solvent, it has an OH right there. And you know that this can participate in hydrogen bonding, so this is going to be actually a polar protic solvent. And when you go back to this, I'll draw in all the implicit hydrogens on the beta carbon. So you can kind of see that this is a pretty sterically hindered molecule. I mean, this is also going to be a secondary, but you have a lot going on here. And based off what our nucleophile is, it's a strong base as well, and you have a polar protic solvent. You can kind of tell that this is going to proceed via an E2 reaction. So what's going to happen is this strong base, it's not going to interact with the alpha carbon directly and displace the chlorine. It's going to interact with the hydrogens on the beta carbon. So it's actually going to come here and extract this hydrogen. The electrons within the carbon-hydrogen bond are going to come and form a double bond, and that is going to displace the chlorine indirectly. And you're going to get a product that looks like this. And then your chlorine is off to the side, floating in space now. And that's basically it. The reaction again is also pretty simple for E2. It's just knowing when to use E2. So if you can keep these concepts in mind about E2 and SN2, it'll aid you a lot when tackling different problems on assessments that your instructors may give you. So it's not really critical to memorize every single reaction mechanism and know if you can identify on an exam or assessment. It's kind of better to apply these principles of when you're going to use SN2 and E2 to kind of govern your thinking and know when you're going to actually use it based off the solvent you're using, how strictly hindered your substrate may be, stuff like that. Keeping that general stuff in mind is much more critical to your explanations and reasonings for problems and actually knowing how to do a problem. So I hope this video was helpful. That's really all I had to cover about SN2 and E2. If you had any other questions, please feel free to drop them down below in the comments. I'll be happy to answer them. And thank you guys for watching. I hope you guys will tune in for the next episode. Thank you.